Wednesday.
Wow, thanks, Jason.
Okay, so these are called related rates. They are what you would commonly call a word problem. They take the calculus concepts that we've talked about and they relate them to real world examples. So you might find this interesting. You might find it kind of silly. I like them because it answers the old question, where am I ever going to use this? So you should be able to find a related rate. You should be able to solve real world problems using what I call a 9-step approach. That seems like a lot, but it'll actually help you it'll guide you through the problem. And then you should be able to enjoy spicy food. Anybody not like spicy food? Really? Not at all?
I mean,
No spicy food?
It gets me nervous.
Spicy food makes you nervous?
it can sense your fear.
Apples also make me nervous. He's allergic to apples.
Oh, well, that I understand, but spicy, you're not allergic to spicy food, are you?
It makes me feel a way that I don't want to feel.
If I wasn't recording, I would pursue this line of conversation, but I'm afraid where it's going to end up.
It's gonna go down a dark path.
Yeah, exactly. And we don't want to be there, not without the dog. Okay, so we're going to use the chain rule. What changes in related rates is that instead of tying everything into x and y like we did here, we're going to tie everything into time. Okay, so our functions will be things like dr dt, dq dt. Okay, so t becomes our variable, and that's what we're going to be working with.
Should we write that all down?
You can if you like, or I can go back. Okay. First example we're going to do is what's called a naked related rates. It doesn't really tie into anything in the real world. It's just a formula or a problem that we're going to calculate. Okay, good. So, suppose x and y are both differentiable functions of t and related by the equation y equals x squared plus 3. Find dy dt when x equals 1, given that dx dt equals 2. When x equals 1. Okay, that sounds like a lot of gobbledygook. However, what we're going to do is use the same implicit approach we used before, except the difference now is we're working with t. So you recall when we did implicit differentiation, if I took the derivative with respect to x of x, it was just a regular derivative. If I took the derivative of y with respect to x, then I had to stick a y prime on the end of it, right? Right?
Right.
Good. The thing that changes here is everything is going to be taking a derivative in terms of t, so that we have to stick a dx dt or a dy dt on the end of it. So we get something like that. That's what we're going to do. We're going to start by taking the derivative of both sides with respect to t. And so what's a derivative of y with respect to t? What's the derivative of y? 1. And since you took a derivative with respect to t, you have to include a dy dt on the end of it. What's a derivative of x squared plus 3 with respect to t? What's a derivative of x squared plus 3? 2x, but you took the derivative with respect to t, so you have to stick a... No, we can't just use the prime now. Now we've got to use the d business. dx dt is correct. Okay, so we get that. How many variables in that final equation? Or I should say, how many unknowns in that final equation? 3. What are they? Nope. dy over dt is one of them. X is the other. dx dt. Now we look back at the original problem. If there's 3 variables or 3 unknowns, if I'm going to be able to solve that, I have to know at least 2 of the 3 unknowns. Do I know that? Yes. I know x is 1. I know dx dt is 2. And therefore, I'm looking for dy dt. Question?
Yeah, I'm just a little confused how you went from that step to that step.
I took the derivative of y with respect to t.
I
So
got that,
Okay, this one,
Yeah,
derivative of that is 2x,
okay.
but I took the derivative with respect to t, so I have to stick a dx dt on the end of it. Okay. We good? Plug and chug, and we get our final answer of 4. Plug in what you know, solve for what you don't know. So the only change in this first problem as it relates to what we've done already, no pun intended, related rates, is that we're taking derivatives with respect to t instead of x and y. Let's do something more exciting though, shall we? Sorry, I keep forgetting about the bottom half of the board. I'll try to remember when I put these things together, move everything up.
What did you solve?
How's that going, Annette?
What did you solve?
The final equations?
Yeah. What did you plug in it for?
I plugged in 2 for dx dt, and I plugged in 1 for x, because that was given information. Okay? Like I said, that's a naked problem because it doesn't tie into real world problems. We're going to, however, look at some problems like this. Water leaking out of a container. What else does it say up there? Racing automobiles, falling ladders. A lot of death and destruction when you're doing related rates problems. Right? People falling off of ladders, cars colliding, airplanes near missing, stuff leaking out of containers. So it gets a little depressing, but you'll be okay. Okay, so here's the 9-step approach. You want to write down all 9 of these steps because when you're doing these problems, if you follow all 9 steps, it will virtually guarantee that you get it correct. Number 1, draw a picture. Now obviously on a naked problem, there's no picture to draw, but in the examples that we're going to do, there should be some kind of picture that you can draw and label it. Okay, so I've got a ladder leaning against a wall. Which one's the ladder? How long is the ladder? How far up the wall is it? How far is the base from the wall? That kind of stuff. Number 2, define the variables. So you throw an x and a y in there. Well, what does x stand for? Does x stand for the height that the ladder reaches up the wall? Does x stand for the distance that the bottom of the ladder is from the wall? Does x stand for the depth of the pool? Does x stand for the radius of the pool? So again, define the variables. What does each variable represent? What do you know and what are you looking for? In other words, what's given information and what am I trying to solve? So in that previous naked problem, we knew dx dt and we knew x. That's what we know. What we were solving for is dy dt. Step 4, write a general equation. We already had the general equation in the previous problem, but when we do these other problems, you're going to have to come up with the equation. And step 4 is usually the hardest part of these problems. However, they're all pretty much formulas or equations that you've seen before. Pythagorean theorem is a common problem. The dirt equation is a common dirt equation. You know that, right? Distance equals rate times time, dirt equation. Yeah, so the equation isn't too bad. This is very important though. Do not plug and chug yet. A big mistake is people want to start jamming information into that equation. You don't do that till later. Step 5, take the derivative. Fortunately, most of these problems, the derivatives aren't that bad once you get an idea of how the system works. They're not much more difficult than this generally or naked equation we did already. Step 6, snapshot. Okay, now the snapshot means at what particular moment in time are we talking about? Okay, so an example of a problem. Kaz is on top of a ladder. The bottom of the ladder starts to slide out and he starts to fall down. As he falls down the wall, there are an infinite number of points along the wall that we can ask questions about. I'm going to ask about one particular question. It might be, for instance, as the ladder slides down the wall, how fast is he going when he's 10 feet off the ground? Or how high off the ground is he when he's doing negative 10 meters per second? That's really fast, but just as an example, that would not end well. Okay. 7, solve. Do the math. 8 and 9 are commonly forgotten. Ask yourself when you're done, does that answer make sense? Okay, so we calculate where Kaz is when he's falling down the ladder. how far off the ground is he when he's doing a certain speed? If we get an answer like negative 34 meters, that doesn't make any sense. If you get a speed that you calculate for a car, and that car is doing 4 times the speed of sound, you probably did something wrong. Again, the single most forgotten thing that can solve a whole bunch of problems is just ask yourself if it makes sense. You might get some answers where I have no idea if that makes any sense, but at least ask yourself the question. And then the last thing is don't forget units. What are we talking about? Are we talking about meters per second? Are we talking about the number of hamsters? Are we talking about whatever your units are, include them. Yeah.
So are we gonna use these 9 steps throughout the whole year? Or are we gonna learn a better way to do it?
No, this is it. This is whenever you do a related rates problem, you're going to do all 9 steps. And especially when you're learning it initially, the 9 steps will help you keep organized. As you get better at it, you may be able to knock a couple of these out. But if you want to stay organized and make sure you cover all your bases, you definitely want to go with the 9 steps. Okay? Let's try it. So we're pumping air into a spherical balloon. We're not making balloon animals. You don't have this one. Because I'm going to take you through this one, and then we'll do one together. So it's inflating. At a rate of 4.5 cubic feet per minute, find the rate of change of the radius when the radius is 2 feet. Okay. Step number 1, draw a picture. There's my balloon. I'm not a great artist. I also introduced a variable. What do you think that variable stands for? Yeah, the radius. I'm also using V for volume, because that's what we're dealing with. The volume of the balloon as it relates to the radius. Pretty simple so far. Step 3. What do we know and what are we looking for? Okay, I know that the change in the volume is 4.5, because you're told that in the problem. What I'm looking for is what's the change in the radius when r equals 2. This r equals 2 represents our snapshot in time, but that comes later. What's step 4? Write a general equation. What's the general equation we're going to use for this problem?
Volume of a sphere.
Volume of a sphere. Does anybody happen to remember the volume of a sphere? Excellent. If you don't remember, it's okay. Most of the geometric problems that you'll see related rates with, they will give you the formulas that you need from geometry. You should remember some basics, like the area of a circle. Thank you, pi r squared. Okay. The area of a triangle, that kind of stuff. But anything like the volume of cones, the volume of cylinders, the volumes of spheres, those kind of things they'll give you. So there's our general equation. 4/3 pi r cubed. Okay, what's step 5? Take the derivative. What's the derivative of v equals 4/3 pi r cubed? Let's start on the left. What's the derivative of v? Is that what it is again?
Wait, where did the 4/3 come from?
That's just the formula for the volume of a sphere. dv dt, good. The derivative of v is 1. You took a derivative with respect to time, dv dt. Somebody else probably said that also, right? Lucas, props for that. Nice job. Did you steal his answer, or did you come up with it on your own? What's the derivative of the right side?
4 pi r squared
Friendship.
Good. 4 pi r squared times friendship.
Times dr.
With respect to t, so it would be d friendship dt.
Times dr.
dr dt, correct. We took the derivative of r with respect to time, so you got to stick a dr dt on the end of it. That gets us to this. Okay, good. And if you look back in the whatever step it is when you listen what you know and what you don't know, we know some of that stuff. What do we know? We know dv dt, and we know r, correct. So this is a general equation. We can answer a question about the balloon at any point in time, but now we want to look at one particular point in time, which we call the snapshot, and that's when r is equal to 2. Okay? So when r is equal to 2, we know that dv dt is 4.5. Notice that that value is positive because the balloon's getting bigger. If the balloon is deflating, it would be a negative answer. That's important because we'll be looking at problems where we're filling tanks with water or we're draining tanks or things are leaking out of tanks. You got to consider plus or minus on those dv dt. All right, so plug that stuff in and solve for dr dt. And we get, where are we at here? Solve, and we get that 0.0, oh, go back. Sorry, too fast. Plugged in 2 for r, plugged in 4.5 for dv dt, and then solve for dr dt. Which is 14 or 4.5 divided by 16 pi, which turns out to be that answer that I had over there, about 0.09. Okay, good. So solve, and we get that. That's step 7. Step 8, does that answer make any sense? I have no idea. I don't know. But at least I asked myself the question. Now I'll show you a trick to figure out the units. What are the units on that thing? Here's the secret to finding units. I solve for dr dt. What are my units on the radius? I'm sorry? Feet. What's my unit of time? Seconds. So therefore my units here would be feet per second. Okay. So you can get the unit by relating back to what we solved for. It was actually minutes. Sorry. I'm a little shaky on question number 8. I have no idea if that thing is reasonable or not. I don't inflate a lot of balloons. Actually, we did inflate a lot of balloons. I'll try it, but I didn't do it.
Is this on it?
Yeah, it's all. Yes, please. Because you look like you got a mustache.
Oh, we were in gym, but there was band
Yeah.
thingies, and then those are black.
like you have a little-
Yeah, that would make sense.
Little evil mustache. I should have not. We could have had more fun with that.
Could have made her do a problem on the board.
And we would have been so happy that she got it right that we all would have taken pictures of her. Come on, let's get a picture of you solving the problem. And then put it on the Snapchat or on the Twitter. All right, this one you have on your paper, I believe. First one, problem number 1. Here we go. For some reason, we're putting water in a conical tank. This happens all the time. People want to turn the cone upside down. Don't do that. Okay, you're going to hold water in a cone like this, not upside down. You're not storing salt. Okay, so we're storing the water in a conical tank. Or whether, is it a tank? Yeah, it's a tank. It could be a Dixie cup or something off of a drinking fountain. But. And again, notice I gave you the original equation for the volume of a cone. Okay. So let's do this. Whoops, sorry. Is that the same problem? Yeah, there we go. Water tank has the shape of an inverted right circular cone, okay, which is a redundancy. All cones are circular. Has a height of 12 and a base of 6 feet. If the water is being pumped into the tank at a rate of 10 gallons per minute, approximate the rate at which the water level is rising when the water depth is 3 feet. This is a little conversion you want to have in your notes somewhere, that how many cubic feet are in a gallon, or how many gallons, well, that'd be how many cubic feet are in a gallon. It's not something you need to memorize, but it is something that pops up every once in a while. That will change if the liquid is different. If it's not water, if we're using, let's say, oil, that equation or that conversion will change. Okay. I don't remember if I have the whole thing in here. Yeah. Okay, so there's my picture. I chose the variables r and h. R being the radius, of the water and h being the depth of the water. Okay, so step 2, define your variables. What's step 3?
Is it saying, is
Say-
it saying the entire thing is 12 in?
Yes, the
So not
measurements that I have here are the measurements of the tank. What
H
I
not
define
what?
the variables as are the variables that relate to the water itself.
Okay.
Okay? What do I know? What am I looking for? What do I know? I know this, which is, how would you define that? dV dt. Is it positive or negative? Positive, because I'm adding water to the tank. What else do I know? I know the water depth is 3 feet. And what am I looking for? The rate at which the water level is rising. Is that dr dt or dh dt? dh dt. So I'm looking for dh dt when h equals 3. Okay, that's my third step. If you want to convert right away, you probably need to convert that to cubic feet per minute so that we're all in the same units. It would be nice to just use 10, but all of a sudden we're going to do that. Remember, AP standard is 3 decimal places on everything, so as we answer that, you got to keep that in mind. Step 4 was what? I gave you the general equation already, and that is the volume of a cone.
Can you go back?
Sure. Sometimes you'll be given the general equation, sometimes you'll have to write your own general equation. And you'll see as we progress through the examples when that happens. Are we good up to this point?
Yes.
You understand where everything came from? Any confusion about anything? Remember that everything relates to time here. Yes, John? It's funny, you should ask that. We'll get there in a second. Okay? Now things turn really ugly. Yeah.
So the dV dt is just the same thing as the rate of change.
Rate of change of the volume.
Okay, and then you can manipulate the variables, like how you change it from dV to dH. Not manipulate, but like plug in a different.
Correct.
Okay.
Okay, we good so far? This formula is a little weird. It's a little weird because I have both R's and H's in the formula. We have 2 different ways to handle this. In my opinion, one way is much easier than the other. So I'm going to show you the easy way first. Hopefully that clicks with everybody. And then I'll show you the nasty way later. And then you can decide which one you prefer. You can use either one. It'll get you to the same point. I don't want an R and an H in that equation. So if I can figure out a way to get rid of one of those variables, in other words, do some algebraic manipulation ahead of time, that would make me happy. In other words, if I could get the volume all in terms of R or all in terms of H. By the way, which one would I prefer in a perfect world, R or H? For those of you that said R, why R? What's that, Max? Okay, and for those of you that said H, why H? Yeah, we're trying to solve for H, so H is actually the correct answer. Is there a way to get rid of the R in terms of H? Well, now we do a little bit of geometry. Similar triangles. Oh yeah. So this is, no, I'm not gonna. So this is a side view of half of the cone. Here's the height of the cone. Here's the radius of the cone. That's why we needed that information. Here's the depth of the water. Here's the radius of the water. Let's see what you remember from geometry. What equation do I get out of that picture? Again, what equation do I get out of that picture? hear some mumblings.
6 over R equals pi over H.
Say again, I'm sorry.
6 over R equals pi over H.
Good. One possibility. There's a couple different combinations there. Good. Radius over radius equals height over height. You could do radius over height equals radius over. Set it up a couple different ways, but we still get that equation. Then how do you solve that? Cross multiply. Okay. So I think this is what you said, right? Radius over height equals radius over height. Do you do 6 over 12 equals R over H? Okay. Regardless, we get the same thing. This isn't solvable, but it does allow me to write R in terms of H. Now, if this is the easier method, you can imagine what the other one is. But yes, you do need to remember similar triangles. Is everybody with me so far? Okay, good. Now what? Max? Plug it in. Take 1/2 H and plug it in for R. Can I go?
Yes, sir.
And remember, you're squaring the 1/2 H, not just the H. Let's clean that up before we take the derivative. This will be easier. Okay, so it simplifies down to that. Again, not horrible. That's pretty easy to take the derivative of. The calculus so far has been easy. It's this nasty geometry and algebra we have to deal with. But the good thing is this is all in terms of the variables that we're looking for. We can work with V, we can work with H. We got rid of that nasty R, and we're good to go. What's the derivative of the left side of this equation? dv dt. What's the derivative of the right side? Pi over 4 h squared dh dt. Very good. Everybody with me on that? For those of you that are visual learners, it's right there. Okay. Derivative of v is just 1 dv dt. Bring the 3 down, reduce the power by 1. Don't forget to stick a dh dt on the end of it because we're taking a derivative with respect to time. Wow, this is fun. All right, what's next? Snapshot, right? Okay, what do we know? Do we know dv dt?
Yes.
What is it?
1.337.
Yeah, but we converted that to
1.337.
1.337. Do we know what h is?
3 feet.
3, because it told us when h equals 3, and that would allow us to solve for dh dt.
I just had a question.
Certainly.
So it says it's 10 gallons per minute, and then it says 1 gallon is.
Yeah, we need to convert. Because you need, everything needs to be in feet. And was it feet in minutes?
Yes.
Yeah, so we need to be in feet in minutes. So you do that conversion early. All right, what's dh dt? 3 decimal places, 0.189 feet per minute. How do I know it's feet per minute? Because h is in feet, t is in minutes, feet per minute. Okay. Any problems so far? Gianna, what's the
I
matter?
just had a question when we did the similar triangle thing.
Yeah.
Why didn't we mark the height as 3? That's what it
Say again, I'm sorry.
For like the similar triangles, we did the smaller triangles R and H.
Yeah.
Why didn't you do it as 3 if that's what the height of it is? Isn't that?
Because that's the snapshot, and we don't want to do the snapshot until after we take the
Oh, okay.
derivative. Okay, that's a great question, and that's a common mistake. If you didn't hear her question, she said, well, why didn't we just plug in 3 for h? Because, again, we're looking at a general equation, and that's the snapshot which comes later. Okay, we having fun yet?
Yeah.
Awesome. Okay, beautiful. Next one. What's that? I don't know, does it make sense? Sure. Again, it's not always going to make sense. I mean, if you, well, okay, what would be an example of an answer that wouldn't make any sense, John?
2,000 feet.
2,000 feet per minute. Good, that probably wouldn't make any sense. A negative answer. If you're putting water into the tank, the height's not going to go down. 0 would probably not make any sense. Okay, so
Maybe
that's,
also
In that situation, that's what I'm looking for. What did you say about elephants?
You said it doesn't make sense.
Yeah, but what did you say about
20 elephants into a mini.
All right, so here's the second approach to it. You don't have to get rid of both of the variables. You could take the derivative as a product rule. Again, just be a mathematical sponge and absorb. I wouldn't even write this down, but I do think I need to show you the other approach so that you understand how it happens. Okay. So don't replace one of the variables and just take the derivative as a product rule. First times the derivative of the second plus the second times the derivative of the first. Then I just clean that up. And then the problem is we don't know dr dt. So now you got to do another equation. So you have to go through and figure out what dr dt is. That came from the similar triangles. 12r equals 6h when you cross multiply. Take the derivative of both sides and we get to that. And you see where this is going. Know where we want to go. Are we in agreement? Good. So I'll just finish this up. You plug that in and then you go to the end. So that says, I should have emphasized the really with an underline or something. I think you find the first approach quite a bit easier. Because you still have to do similar triangles in the second approach. It's just you're solving for dr dt and dh dt, which is too much work. Okay, next one. We have 1 o'clock. Ship A is 25 miles due south of ship B. Okay. So ship A is due south of ship B. It's here. And then it starts moving west at a rate of 16 miles per hour. Ship B is sailing south. So A started here. And as A moves to the west, B is coming south. So they're doing this. A is moving slower than B. B is sailing at a rate of 20 miles per hour. Find the rate at which the distance between the ships is changing at 1:30. So first question, do you want to work in minutes or do you want to work in hours?
Hours.
Tell me we work for weeks.
Let's suppose we work in hours. Are these okay?
Yes.
What are you going to do here? 0.5. Let's suppose you want to work in minutes. This would be 30, but now you got to change the units on this. I would recommend working in hours. Okay? We good so far? Already drew the picture for you. You're welcome. I do have some variables in there. We need to define those variables. What's x?
16 rate of which?
Nope.
Is it just 16
Eight.
The distance.
Eric?
How far west it is?
How far did it says sailboat? Ship A move? Good. It's a distance. What's y? Distance for ship B. What's z? Distance between them. Okay, so you can see what's going on here. As these ships start, they're going to have a rate or a distance between them that's changing over time. When t equals 0, what's z? Let me say that again. When t equals 0, what's z? 25, right. B's here, A's here, that distance is 25. So notice what I did in the picture. I did a little bit of manipulation for you. If the distance that B traveled is y, then the distance it still has to travel to get down to that point is 25 minus y, because the whole distance is 25. Are we good?
Wait, what did you say when it equals 0? What is z?
When the problem starts, B is here and A is here, so the distance between them, z, is 25. Is that height?
Where do we need 25 minus y?
You'll see in a second. Okay. I don't know if I did. Oh, I didn't do the whole thing, so I'm doing this one now. Okay. Let's see. Got the picture. X is equal to distance for ship A. Y is equal to the distance for ship B. And Z is the distance between ships. That's step 2, right? Correct, I mean?
Yes.
What's step 3? What do we know? What are we looking for? Well, I know that ship A is traveling at a rate of 16 miles per hour. How do I express that mathematically or calculus-wise? dx dt. dx dt is equal to 16 mph. Is that a positive or a negative value?
Well, it's a speed, not a velocity. Or it has to be positive.
Well said. Why is it positive?
Because it doesn't have a direction.
No. Because x is getting bigger. Okay. What else do I know? I know dy dt is 20 mph. Is that positive or negative?
Positive.
It's positive because y is getting bigger. We're getting better. What are we looking for? We're looking for dz dt. dzt equals, I don't know, when t equals, what do we decide? 0.5 hours. Awesome. That's step 3, correct? Step 4? General equation. What general equation are we going to use here? Pythagorean theorem. Good. So that general equation would be x squared plus the quantity 25 minus y squared equals z squared. That's why I needed the 25 minus y. Not to completely confuse everybody, but I could have set the problem up differently by calling the distance from B to that point y, but I don't want to go there, it'll just confuse you. Is everybody okay with the 25 minus y?
Yeah.
Awesome. Step 5.
Take the derivative.
Derivative, here we go. What's the derivative of x squared? 2x dx dt. Plus, what's the derivative of 25 minus y quantity squared? You missed something. Yeah, good. We got a -1 in there. Would it be better if I move this up? Okay, let's do this then. Let's go to, no, I wanted that on and I want to go here. There we go. Okay, x squared plus 25 minus y quantity squared equals z squared. Is this better?
Yeah.
Good. 2x dx dt. Let's do this one again. Bring the 2 down, reduce the power by 1, which makes it 1. What did you miss? You missed the -1 from the chain. So this becomes negative 25 minus y quantity times dy dt. Oh, forgot the 2, right, thank you, good. And derivative of z squared, 2z. dz dt. If you'd like, you don't have to, but if you'd like, we could get rid of all these 2's. Is that okay? Everything's multiplied by 2, might as well just get rid of it. That, I believe, was step 5. Step 6. Snapshot. Okay, so at what period in time are we now concerned about the boat or ships being apart? When t equals 0.5. So, do we know what x is when that happens? Uh-oh. Oh, we can. Let's go back. Whoops, wrong way. Let's go back to this problem. What I'm missing is x, y, and z at the snapshot. So if ship A is traveling at 16 miles per hour for a half hour, what's x? 8. Are we all good with that? Yes. Answer carefully here. If, well, let me just answer the question. 20 miles an hour for a half hour? 10. So y is equal to 10. How do you find z? Pythagorean theorem. This distance would be 15.
No. Oh, yeah.
Yeah. And then we do Pythagorean theorem. I call that a sidebar. So you come over on the sidebar and you figure out 8 squared plus 15 squared is equal to z squared So z is equal to
13?
can't be 13.
2 root 7.
You have calculators. What's the square?
17.
Yes, it is 17. Also known as a Pythagorean triple. It won't always work out that way. Okay, so do you have those things written down so I can go to the other slide? All right. That's not the slide. This is the slide. Beautiful. What's x? 8. What's dx dt?
15.
What's y is 10, so that's going to be 15. What was dy dt? Is that 20? And z was 17, and therefore we have dz dt. Beautiful. Solve that for dz dt, please. Sorry? Yeah, hold on. Let me finish this. Stay focused. Let's get this done. We'll take a consensus on this one. I'm sorry? Okay, we'll go with that. Negative 10.118. Again, 3 decimal places because it's the AP standard. Does that answer make sense? Yeah, sure. The distance between them is getting smaller for some reason. That's okay. Is that a reasonable rate? Well, if the boats are going at 16 and 20, that seems reasonable. An unreasonable answer would be like 400 or, some incredibly large number. And the last part, what are the units? Miles per hour. Z is measured in miles. T is measured in hours. mph. We're all done.
Surprised they're not using knots.
I'm sorry?
I'm surprised they're not using knots because they are ships, right?
Wow. That was nerdalicious. Well done. Excellent. Okay. We're running out of time here, so we'll save the, what do we got on the back?
The ladder.
We got a ladder, and then I probably want to do a leaky bucket problem with you also tomorrow. So I'll go through a couple more examples. Start on the problems tonight. Try to stick to the 9-step approach. The only time that won't work, really, is when you're looking at the naked problems. But when you get into these related rates word problems, stay with all 9 parts, John. That would be the first day of 2-6. I'm not sure what day it is. Martina, you wanted to see the other page?
Actually, I figured it out.
You're good? Okay. Can I erase this?
Yes,